So we have seen that there's a relationship between a space X and the corresponding group pi1 of X, the fundamental group of X. And I want us to explore this a little bit more today. So given a space X, a topological space, we can calculate the fundamental group. It depends on your base point, but if it's path connected, then you can pick whatever base point you want, and it's independent of your choice. So we'll just assume we're working on some path connected space. Otherwise, you can be intentional to record your base points. Great. So that's how you move from a space to a group. What we're going to think about today is what if you have a map between two spaces? Let's say you have a map, phi, from some space X to some space Y. Then what we're going to see today is that there is an induced map from the fundamental group of X to the fundamental group. If you want to, you can record the base point, right, X naught, to the fundamental group of Y with its corresponding base point Y naught, where Y naught is just the image of X naught, right? And so we're going to try to understand how maps over here lead to maps over here. So in 1 second, I'm going to try and define this induced map on the fundamental group. But before I do, let me just give you a few reminders. In this class, I'm always thinking about continuous maps. So this is going to be continuous. And well, let me just define it. So this induced map will be defined as follows. I'll just define it here. Given some element of pi1 of X, so that's a loop. This is F, where F is some loop. It's the equivalence class of some loop up to homotopy. This is some loop up to homotopy in X. We're going to map that to just wherever phi takes the loop F and look at its class up to homotopy. So phi takes things in X to Y. So you can take this loop to make it some loop in Y, and it's still defined up to homotopy. And so the first thing you should ask about this definition is this well defined? Is this well defined? Okay, what do I mean by that, and why do we need to ask this? Well, here, I might have two different loops that are in the same equivalence class. For example, if I have some F0 that's homotopic to F1, then the equivalence class for F0 will be equal to the equivalence class for F1. So now what we need to do is we need to check, is it true that when I map that F0, will I get the same thing as when I map that F1? And I should, because these classes are equal to each other. But it's not obvious, because the way we define this guy is we just define him to be the image of F0. You just map the F0 over. Whereas him on the right is just the image of F1. So we need some way to convince ourselves that these are actually equal to each other. Well, let's think. What does it mean for these to be equal? The real question is, are these equal? But for those to be equal, what we need is some homotopy between the image of F0 and the image of F1. Can anyone suggest what the homotopy might be? Well, I'll just come back here. Since these guys, F0 and F1, are homotopic, you already have a homotopy. ft. And so what should we do with that homotopy? Just do the obvious thing. We're just going to look at the composition phi of ft. Since we said phi is continuous, we know this composition is continuous, and so then that gives me the homotopy I needed. So sure enough, these end up being equal as desired. So this was just a little technical detail to check, but now we see that if we have a map from one space to another, it gives us a map from one group to the other group. Nice? Okay. Well, now that we have a map between two groups, what might you hope to be true? You might hope it's a homomorphism, right? So let's check that. You might hope that this induced map is a homomorphism. So this is an induced map from pi1 of x to pi1 of y. You might hope this is a homomorphism. And indeed, that's true. So let's show this really fast. How do we show this? Well, we want to show that the induced map on fg, so what's going on here? This is an element of pi1 of x. This is an element of pi1 of x. And I'm taking their product in pi1 of x, right? What I hope to show, I need to check is this equal to the induced map on f times the induced map on G. Where this product right here between these is the product of the elements in pi1 of x. I won't write it, but these are being multiplied in pi1 of x, where these are being multiplied in pi1 of y, right? Okay. So let's just check to see if those are equal. First of all, what is f times g? Do you remember how we defined this for the fundamental group? What's the binary operation of the fundamental group? Yeah, this is just the equivalence class of f dot g up to homotopy equivalence. So we just have the induced map on the equivalence class of the product, the path product of f dot g. Where this means first you do f in the first half of time, and then you do g in the second half of time, right? Okay, now what do we have? Well, this just comes out to be, by our definition of the induced map, phi of f dot g. Here on the right, we have phi of f multiplied with phi of g, which will just be the path product between phi of f and phi of g. Let's think about what this guy's telling me. Here I do f from time 0 to 1/2, then I do g from time 1/2 to 1, and then I map that over into y. So I'm mapping that whole loop. Here, I do the image of f from 0 to 1, and then I do the image of g from 0 to 1/2, and then the image of g from 1/2 to 1. And those are exactly equal. These are in fact exactly equal. These values are exactly the same thing. The image, f dot g, if you think about it, is just exactly, you're just going to map along the f, then along the g, which is the same as exactly mapping the f, and then doing the product of the map of the g. So those are exactly equal to each other. So indeed, you have equality here. So yes, these are equal. So yes, it's a homomorphism. So now instead of calling this the induced map, I'm going to call this the induced homomorphism. Good? Okay. There are a few more properties of this induced homomorphism I want to mention. And let me just do it right here. We now have that it's well defined. Let me mention just a couple more properties of it. that will be helpful. If you have two maps, so let me write this out. Let's say you have pi1 of x. If you want to include a base point every time you can, I just find it tedious, so I tend to drop it, to pi1 of y. And then you have some other map to pi1 of a topological space Z. So let's call this guy phi and this guy psi. Then, together, this is the induced map phi, and this is the induced map phi, right? So I'm thinking down here, I have some space x that maps to some space y via phi, but then I have some psi that maps y to z, and that induces these maps up here. Then I have this composition, which is just going to be first do the phi, and then do the psi. And up here, I'll get the induced map of psi composed with phi induced. I claim that this composition, psi composed with phi induced map, is the same as, so going from here to here is the same as first looking at the induced map of phi, and then looking at the induced map of psi. So just how this is the composition of these two, I claim this guy will be the composition of these two. And this just requires us to unpack the definition one more time. So to show that two maps are the same, you show that those maps do the same thing to any element you start out with. So if you begin with some loop f inside of x, then you have some homotopy equivalence class of f up to homotopy inside of pi1 of x. So this is an element of pi1 of x. And so I can ask, what do both of these things do to f? So I want to check that these are equal for all f, loops f inside of x at whatever my base point is. So that's what I want to check. So here we go. This guy on the left is some induced map of f. Remember, a definition is when you have an induced map, you just move it to the inside. So this just becomes psi composed with phi performed on f, or composed with f. Just going to do this composed with f. So really here, there's a composition. I'm not writing it every time, but these are being composed together. So sometimes I'll just drop the composition. I'm just saying, first to the f, you're going to do the composition of phi and phi. Here on the right, this composition is the same thing as saying this induced map of this induced map of f, which is the same thing as saying psi star, the induced map of psi, of phi of f. But that's equally just the same thing as psi of phi of f, equivalence class. And then, by the associative property, these are just equal to each other, right? First performing phi to f and then performing psi is the same thing as performing this composition of f, this composition of f. So indeed, these equal. The last thing I'll note, and I'll just squeeze it in down here, is if I have the identity on, say, some space x, so if I have a map from x to itself, that's just the identity map, then you tell me, what is the induced map going to be on your pi1? Well, it's the induced map of identity, right? It's this induced map of identity. So this is pi1 of x, the corresponding induced map. But what is that going to be? Well, anything in here, you just perform identity to it. It stays the same. So that's the same as just the identity on pi1 of x. So the induced map of identity is just the identity as well. This induced map is itself just the identity map. Okay. So here I've just given some properties. Cool. The big thing I want to prove today, and it won't take us long at all, we'll do it very quickly, but I want to show that in certain situations, not only do you have that this is a homotopy, not only do you have that this is a homomorphism, not only do you have that this is a homomorphism, but you can actually have something stronger. If your spaces x and y look like each other, then in fact this map will come out to be an isomorphism. So it's a homomorphism. And remember, homomorphism, if it's bijective, is an isomorphism. So I want to look at times when, based on the relationship between x and y, this induced map is not just a homomorphism, but in fact comes out to be an isomorphism. And the first time that happens is when your x and y are homeomorphic to each other. So what do I mean by homeomorphic? We call x and y homeomorphic if there exists a bicontinuous map, or that is a continuous map, a continuous bijective map with a continuous inverse. So in a second, I'll show you that if this is homeomorphic, it implies this is isomorphic. So the first big result today is we're going to see that if x and y are homeomorphic, that implies your pi1 of x and your pi1 of y are isomorphic. But I realize I'm throwing a bunch of words at you right now. So let me try to give you some examples of things that are homeomorphic or not homeomorphic, right? So I'll give you some examples of quick maps, and you just tell me if each one is homeomorphic or not homeomorphic. So here's the first one. Let's do, here's a good one. Let's think about the map, I'll call it phi, sure, from the real numbers to S1, where here I'll think of S1 as being like the unit circle sitting inside of R2, defined by a number t goes to the coordinate pair cosine of 2 pi t sine of 2 pi t. Here R is just the helix that's sitting on top of S1. That showed up in the proof that pi1 of the S1 is isomorphic to Z. So here we have such a map. Is that is this a homeomorphism? Why not? It's not bijective. Yeah, this is not injective. This is not injective. Right? All of the integers get sent to 0, 0. No, all the integers get sent to 1, 0. Right? So every integer n gets sent to the point 1, 0 for all n. So this is clearly not a bijection. Okay. Let's pick something that is a bijection. If you want a bijection, you might say, well, what if we limit our attention to just the interval 0, 1? And we keep the map exactly the same. 0, 1 to S, not even including 1, because I don't want both 0 and 1 to map to the same place. So just the half open interval, where it's closed on the side of 0 and open on the side of 1. That again sends t to cosine of 2 pi t and sine of 2 pi t. So if you want a visual of this, it's taking 0 to 1, and it's stretching it around the circle. Stretching it around the circle. Is it continuous? Is this map continuous? Yeah, you take 2 points close to each other, they end up close to each other, definitely continuous, so that's good. Is it bijective? Yeah, each point here maps to a point here. So is it a homeomorphism? No, why not? The inverse is not continuous. If you think about the inverse, you think about like what happens to this point 0, a 1, 0, like 1, 0, and a point just below it. And you see 1, 0 gets sent back here, whereas the point just below it gets sent over here. So it's not a continuous inverse. Okay. Let me give you one last example. Let's think of the map from, I had thought of some good ones. Oh, here's a nice one. From the open interval 0, 1 into the real numbers. Can anyone think of a nice bicontinuous way to do this? How might you do this? Where might you send some point t? Something like tangent takes an open interval. In that case, it's negative pi over 2 to pi over 2, and stretches it out to be the whole real numbers, right? So we can first map this to be the map to take it to first negative pi over 2 to pi over 2. So we can define that to be negative pi over 2 t plus pi. That map is going to send this to be from negative pi over 2 when you're at 0. No, that doesn't quite work. Pi over 2 minus pi, that's backwards. Pi over 2 minus, negative pi over 2 plus pi t. Did I do that last time? Anyway, when you're at 0, you're at negative pi over 2. And as you grow to 1, you approach positive pi over 2, right? And then, now that you've stretched to be the interval negative pi over 2 to pi, if you apply tangent to that, that will stretch it to be all the real numbers. And this is a homeomorphism. This is a homeomorphism. And typically in topology, we think of things up to homeomorphism. If two spaces are homeomorphic, we think of them as the same. The open interval 0, 1 is like R, where you never quite get to 0, and you never quite get to 1, just like you never quite get to negative infinity, and you never quite get to infinity, right? And that tangent is the way to think about stretching this onto that. Good. Which means the fundamental group of this open interval should be the same as the fundamental group of R. That's what this theorem is saying. That the fundamental groups are isomorphic. So recall the difference between a homomorphism and an isomorphism. If you have something like just the map Z maps onto Z mod 3Z, 3 mod, Z mod 3, that's just the numbers 0, 1, and 2, with like the mod 3 map. This gives you a homomorphism that's not an isomorphism. This gives you a homomorphism, but it's not an isomorphism. Whereas we've seen if you have something like pi 1 of S1, it's isomorphic to Z. The values of this correspond exactly to like your 1, 2, 3, 0, -1, -2, -3, right? So isomorphism is you need both a homomorphism and for it to be bijective. This is not bijective. Here, many things could send to the same value. Like here, 17 and 7 and, oh no, that's not how math works. 17 and 2 both map to 2. Yeah. So that's not an injective. This guy is injective. It's a bijection. So this one over here is an isomorphism. When two spaces are homeomorphic, I'll use the notation X is homeomorphic to Y, which is the same as my notation for groups being isomorphic. So it's highly suggestive that I use the same notation. In fact, some people refer to a homeomorphism, there's an extra E here, a homeomorphism. Some people refer to this as a topological isomorphism. Just for various historical reasons, the word that kind of stuck was homeomorphism. It'd be nice if we called it an isomorphism. This is an isomorphism of spaces. This is an isomorphism of groups. But I'll tend to use the homeomorphism to mean the isomorphism of spaces. But now let me prove that if in fact your spaces are homeomorphic, there's a continuous map from one to the other, and there's a continuous inverse, so it's a bijection, then it gives you a isomorphism of your fundamental groups. So let's prove that and then see some of the consequences of it. Okay, so here I define my induced homomorphism. I'm going to come over here and show that my induced homomorphism is actually an isomorphism. So let me write this out. Theorem. If I have some map that takes X and some corresponding base point to Y and some corresponding base point, and I'm just keeping track of X naught's the point that gets sent to Y naught. Often I'll ignore my base points. I'm just trying to be complete here. If this map is a homeomorphism, then the induced map from pi1 of X, base point X naught, to pi1 of Y with base point Y naught is an isomorphism. Okay, so how do we do this? Proof. We already know this is a homomorphism. This is always a homomorphism if you have a continuous map. So what we need to show is that this induced homomorphism has an inverse. Because if it has an inverse map, then it's bijective. If this has an inverse, then we know it's bijective. You can't have an inverse if you're not bijective. If you're not isomorphic, if you have two guys going to the same place, the inverse won't be well defined, because that guy doesn't know which one to come back to. And if you're not surjective, then you can't have an inverse because it won't be defined on the whole domain. So showing something's bijective is the same as finding the inverse for it. Okay, so when you show this guy has an inverse, how could we possibly do that? Well, we have that this is a homeomorphism. So we know that this map phi from X to Y has a continuous inverse. We'll just call it phi inverse that maps from Y to X. And since that's a continuous map, there's an induced map. Thus, we have an induced map by just looking at the induced map of the inverse from pi 1 of y, I'm losing track of my base points, but you can record them each time if you want, to pi 1 of x. And I claim that this induced map is the inverse of this guy. So I claim that the inverse of the induced map is just the induced map of the inverse. How do we check that? Well, we check it by showing that this induced map, when composed with this induced map, will give you the identity. So the way we check this claim is we say, oh, what do I get when I compose this induced map with the induced map of its inverse? And you have from before this nice property that we showed, that when you're composing two induced maps, it's just the induced map of the composition. So when I'm composing these induced maps, this is, put it right like this. This is just going to be, the induced map of the inverse. This is just going to be the same thing as the induced map on phi compose phi inverse. But those inverses, so that's just our density, so that's just the induced map on the identity, and we said the induced map on the identity is just the identity. Well, this shows it's a right inverse. You can also check that's an inverse on the left side. There were some funny cases where it would be an inverse on one side but not the other. That's like if it's injective but not surjective, so you really need to check both sides, but it'll be exactly the same. There's nothing special here. You just check on the other side by the exact same reasoning. It's also identity. So it's both a left and a right-sided inverse. So sure enough, this guy has an inverse, and hence he's an isomorphism. Yes? I had a subscript somewhere that got wrong. Oh, yes, this is phi inverse. Thank you. Thank you. Great. Good? Okay. So I've thrown a bunch of words at you. Like, what is this good for? So let me give you a few consequences of this. So we know that homeomorphic spaces have isomorphic fundamental groups, where homeomorphic is just me saying if two spaces are the same up to a bicontinuous map, a continuous map with continuous inverse, then the fundamental groups are the same, the isomorphic, which is the same. Nice bijective pairing between them that preserves the binary operation. So let's look at some consequences. Here's the first consequence. Proposition. The fundamental group of Sn is trivial. Some people put 0 for trivial, sometimes I put 1. I'm going to put 1 here. By this I just mean the group with one element. The fundamental group of Sn is trivial, or isomorphic to the trivial group, but there's only one trivial group, right? The group does one element. Is isomorphic to the trivial group whenever your n is at least 2. If n is 1, we know this is z, right? So it's clearly not true for n equals 1. For n equals 2, this is a sphere. For n equals 3, it's a higher dimensional sphere. And we're just claiming in all those higher dimensional cases, it's trivial. And we kind of already know this because it's like, well, in the case n equals 2, all you're saying is any loop that you have, let's say your base point's right here, any loop so there's some loop. Any loop that you have can just be pulled down to the trivial loop. And so I think intuitively this is quite clear. And maybe you believe if you have higher dimensional spheres, it's still true. But let's try and justify this. So here's how to think about why this is true. So if you're given a loop, it's some map from 0, 1 into a nice continuous map into Sn. I claim that you can always find a point that the loop doesn't hit. You can't do that in S1. In S1, your loop could hit all the points in S1. This is why this breaks down in S1. But in S2 and so forth, there's always some point. You can find some point that the loop didn't hit. Your loop doesn't fill up all of the surface of Sn. So you can find a point x in Sn not on the loop. For convenience, I'm just going to put this point at the North Pole right here. It may not be at the North Pole, but you can just slide it over a little bit. Okay. If you're not fully happy with this, there's a full justification in Hatcher for why this is true, but it gets a little bit technical. Imagining, what might your loop look like, and convincing yourself that you can always find a point. Or, if the point you want to take in, you could just move a little bit over, and you can find a point. So there's always some point not in the loop. Now, what I want us to do is let's think about what is Sn minus that point. So let's come back to this case of S2. Can you tell me what is S2 minus this point? What is it homeomorphic to? What space is it equivalent to removing one point from the sphere? R2. You could say D2 also, but R2. Well, you could contract it to D2, but it's homeomorphic to R2. And the way to see that is the classic example of something called stereographic projection, where from this North Pole, you have your sphere like sitting above R2. So here's your S2, here's your R2. And just from the North Pole, you imagine them being like a light there. And the light, you just shine down. And at some point, it'll hit the sphere. And then as it keeps going, it'll map into some point on R2. And convince yourself by doing it this way, point on the bottom, go straight down. Points that are quite high up become points very far away on R2. And convince yourself every point on R2 gets mapped bijectively in a nice continuous way to every point on the sphere minus the North Pole. The North Pole doesn't have a point that it goes to. Right, so this is called stereographic projection. Stereographic projection. Sometimes we don't know how to spell a word, I kind of just make it messy. But, okay. So these guys are equivalent. Which means, since the corresponding fundamental groups have to be isomorphic, your F is trivial in R2. We know that F is trivial in the fundamental group of R2. Hence, we know your F is trivial in the fundamental group of Sn minus the point, because these fundamental groups are isomorphic. So if he's 0 in here, he must be 0 down here. But that means there's some way to shrink the loop F down to a single point in Sn minus x. But if you can shrink it down to a single point in Sn minus x, then you can shrink it down to a single point inside of Sn. Right? So the idea is this loop gets mapped down here to some loop in R2, or more generally in Rn, and more generally in Rn. In Rn, you know already that the fundamental group of Rn is 0, so you can shrink them down to a point, but then just do the corresponding operation up here. And that'll shrink it down to a point, avoiding the North Pole. Good? Cool. So we're starting to hopefully see the power of moving from a space to a homeomorphic space, knowing that allows you to move from a fundamental group to an isomorphic fundamental group. This is a cool little fact, that only S1 has pi1 non-trivial. All the other ones is trivial. Let me give you one more fact that we talk about what it means. Maybe it's obvious, but it's not obvious how to prove it. Proposition. R2 is not homeomorphic to Rn if your n is not equal to 2. Of course, if n equals 2, you don't have any problems. Okay. So this might take some convincing. Like, how do you know that R1 is not homeomorphic to R2? Well, if it was homeomorphic, you would have these nice bicontinuous map. You would have a map and its inverse. So you would have some nice continuous map phi in its inverse, phi inverse. That would let us move between these guys, right? And I don't know, like you might try and do something like, oh, there can't be a bijection, but like both of these have an uncountable number of points, and so that's not going to quite help you see it. It's like, how can you tell these are different? It's actually a really clever argument. The way you can tell they're different is because if you remove a point from R1, and you remove a point from R2. So here I'm just going to remove some point x. Here I'm going to remove the corresponding point, whatever phi of x is, phi of x. What happens? Here I have R1 minus the point. Here I have R2 minus the point. In both cases, this is just a point. This is just a point. If these spaces are homeomorphic, then they should still be homeomorphic, because I still have the exact same map between them. And I've just removed corresponding points from each one. But I claim they're not homeomorphic. Why? Because there's something true about this space that isn't true about this space. In particular, this space on the right is path connected. It has one path connected component. Here on the right, it got split into two different components. This is not path connected. This is not path connected. Like, why is that a contradiction? Because if you had two different points here, one on the right-hand side and one on the left, those 2 points would map over here to 2 points. But there should be some path that connects those that doesn't touch your missing point. And then you just ask, okay, apply your inverse map to that path, and it should give you some path that connects these two. But they're on different sides, so they're in different path components, so they're not connected. So there can't be a continuous map going both ways. Okay. We understand that argument? So this is enough to show. So this shows So these are not homeomorphic. Not homeomorphic. Homeomorphic. So that's enough to show that your R2 is not homeomorphic to R1. Well, we're going to do a very similar argument, but we're going to need a little more powerful tools, in particular the fundamental group, for when n is bigger than or equal to 3. So this takes care of the case n equals 1. Let's think about the case n is greater than or equal to 3. If R2 is homeomorphic to Rn, then R2 minus a point would be homeomorphic to Rn minus whatever the corresponding point is. But what is R2 minus a point? What's it homeomorphic to?
It's homotopy equivalent to S1 is not homomorphic.
Ah, good. So let's try and think about what this is homeomorphic to. So here's R2. Yeah, this isn't obvious. Here's R2. And I've removed a point. The way you can think about this, like imagine it's the origin, just for simplicity. Remove the origin of R2. So Cartesian coordinates, remove the origin. Then every point in R2 can be described by describing the angle it's at on the unit circle, where on the unit circle it's at, and how far away it is. Right? It's like how you learn every point is described by an angle and its radius. So complex analysis, you do stuff like this, right, in complex plane. So every point is just, and these are going up to but not touching the missing point. Up to but not touching the missing point. So I claim that this way of thinking helps you see that R2 is secretly, minus a point, secretly S1 cross R, where each of these lines is homeomorphic to R. Remember, an open side is the same as like going off to infinity. So even though like it stops just short of this point, because it's open here, it's approaching this point, but never quite gets there, that's the same as going off for infinitely far. This is like showing that 0, 1, or in this case it would be like going open interval 0 to infinity is homeomorphic to all of R, right? You can think of each of these as being like the interval 0, infinity, and I'm just saying that's homeomorphic to R, just like 0, 1 was, yeah.
You can like remove a point from the sphere since the sphere is homeomorphic to R2.
Remove a point from the...
2 points from the sphere, so get a point with this.
Oh, that's fine too. Yeah, you're saying that another way of thinking about this is it's a sphere minus the north and south pole. Yeah, and minus the north and south pole is like you have S1, the equator, and then it goes arbitrarily high up and down, approaching but never quite reaching the north and south pole. That's another way of visualizing it, yeah. So however you visualize it, these are equivalent. And more generally, this would be homomorphic to just Sn minus 1 cross R. Right, in the case of like, so this was R2 minus a point. In the case of like R3 minus a point, you should think, so here's like all of three-dimensional space. You can think, well, there's this unit circle at the center, right? And then the center's been removed, but any point is just somewhere in a direction in the unit circle with some distance on one of these rays that go in every direction. So these are my R's. So this is R across Sn minus 1 in general. Okay, great. If you believe that, then we have well, I'll just do it here for economy. If we start taking pi 1 of these guys, the pi 1s, the fundamental groups, should be isomorphic. Okay, now I'm going to need one tool, which we haven't talked about, but it shouldn't take too much to convince yourself of it, or maybe it will, but you should convince yourself of this. What is the fundamental group of a product of two spaces? I claim that this is just isomorphic to the product of the groups of the spaces. So this is maybe not obvious, but what this is saying in particular, for example, would be that pi 1 of, say, S1 cross S1, recall that's just the torus, is isomorphic to pi 1 of S1 cross pi 1 of S1. Ran out of room there. Which is just Z cross Z. So what is Z cross Z? Z cross Z is just a group of pairs Mn, where both your M and your N are in Z. And then the group operation, just like typically your group operation Z is addition, is just coordinate addition on these, right? So with addition, defined the obvious way. How do you show this? Well, what you have to convince yourself of is that a homotopy in X cross Y is just two homotopies, one homotopy in X and one homotopy in Y put together. So you should convince yourself of this. But I mean, this should be hopefully believable, right? Like if you see the torus, it's telling you that for every pair, there is a homotopy class, an equivalence class up to homotopy. So for example, a ring around once like this would be like 1, 0. And a ring around once like this would correspond to 0, 1. But you could also get cool combinations of the two. So let me try and draw you a cool combination of the two. This is becoming a little lengthy aside. Like, how can you be going around both looping one direction and the other direction? How can you loop around both circles? Well, here's one guy that would do that. Okay, I have a PhD in knot theory, so I should be able to draw this. If not, I feel like I get my credentials revoked. That's what I want to draw on the torus. You know what? We're going to cheat. We'll first draw the knot, then we'll draw the torus. Let's take a look at this guy. How many times does he go around this way? Here, he's like on the side, he comes on top, and then he passes below. Okay, so to pass below, he really needs to like pass below. So now he's on the bottom, and then he comes back up to the top. And then he goes on bottom. So to go on bottom, he really needs to, there you go on. He goes on bottom, and then he comes back on top. And then he comes back and bottom. Was that 3 times around? Did we count that right? So we go from the top to the bottom to the top to the bottom to the top. I think it was 3 times around. How many times did it go around this way? We went once around, twice around, so 3, 2. 3, 2 gives you, it's called the trefoil knot. And the trefoil knot is a special case of a torus knot. If you select relatively prime numbers, you can create a knot this way that corresponds to an element here. If they're not relatively prime, you get it crossing over itself. It gets a little bit more messy. But you can still draw the loop there. Okay. If you accept this property, then you simply have that this is pi 1 of Sn minus 1 cross pi 1 of R. And likewise, this is pi 1 of S1 cross pi 1 of R. But here, pi 1 of R is trivial. And crossing with trivial is like crossing with a single point. It doesn't add any richness to your group. This group is just isomorphic to pi 1 of Sn minus 1. And this one's just isomorphic to pi 1 of S1. But we know when n is greater than or equal to 3, this guy is trivial. Because this would be S2 or higher. That's what we just showed. Whereas we know this guy is Z. So we showed Z is isomorphic to 1. Well, that's a contradiction. So these guys must not be homeomorphic. Otherwise, you get this contradiction. Contradiction. Okay. So let me say 1 or 2 more last things in the last 5 minutes. Come back to our big story. Here we're saying if 2 spaces are homeomorphic, that implies the fundamental groups are isomorphic. Now, a minute ago, someone mentioned something. When I was asking, what is like R2 minus a point the same as? You said, well, it's not quite homeomorphic, but it is like just S2. Like there's a sense that R2 minus a point is quite similar to S1. Do you remember the relationship between these? If I have R2 and I omit this point in the middle, and then I have S1, what's the relationship between these spaces? It's not a homeomorphism. The inverse map won't be well defined because you're sending a whole bunch of different points. All these points are getting sent to that one point. So there's not a well-defined inverse. But what do we call S1? It's a homotopy equivalence, a special kind of homotopy equivalence. It's deformation retract. And so you might first try to show, well, is it true in general that if X is a deformation retract of Y, if there's a deformation retraction between X and Y, deformation retract, is it still the case that your pi 1's isomorphic? But I'm not going to prove that because something even more general is true, and that is if X and Y are homotopy equivalent. Are homotopy equivalent, which is a more general notion than deformation retract, then that gives you that these are isomorphic. So a homeomorphic is a special case of deformation retract, is a special case of a homotopy equivalence. And so the more general form of the statement is you actually just need your spaces to be homotopy equivalent to get that the fundamental group is isomorphic. So let me just take like 2 or 3 minutes to tell you why that's the case to wrap up. So our theorem that we want to prove to conclude is that if x and y are homotopy equivalent, then pi 1 of x is isomorphic to pi 1 of y. So this is much looser than having to be homeomorphic. Let's remind ourselves what we mean by a homotopy equivalence. If x and y are homotopy equivalent, that means that there's some map from x to y, and there's some map from y to x such that, can you remind me what it is? Such that what is true? It's not that this is an inverse of this map. It's weaker. It's that the composition is just homotopic to the identity. It's not that it's equal to identity, it's homotopic to the identity, where this is first going to be, so this is a map from x to y to x, so it's the identity of x, and likewise the composition the other way of v composed with c is homotopic to the identity on y. That's my definition here. So let's try and see why this is an isomorphism. Well, we have an induced homomorphism from pi 1 of x to pi 1 of y. And of course, you also have an induced homomorphism from pi 1 of y to pi 1 of x. And wouldn't it be nice if this serves as the inverse of this guy? So let's check. What is going to happen if I first do my induced map phi and then my induced map c? Well, that composition of maps is the same as just c composed with phi, induced map. But like here we really need to think, what is this induced map? So like let's have the map do something to some element f. That's just going to give me phi c of phi of f. But phi of c is homotopic to identity. And this is the equivalence class up to homotopy. So this is the same as just the identity on f. Hence, this map here is equal to just doing the identity map on f. So he really is acting as inverse. And likewise, you can go the other direction, it's the exact same argument. Likewise, this will just be identity as well. So, although C and phi are not inverses of each other, the induced maps act as inverses of each other. Because the induced maps are working in pi 1, and pi 1 you're looking at equivalence classes up to homotopy. So it's good enough that these are inverses up to homotopy. And that's why homotopy equivalence gives you isotopy. So this is the last thing I'm going to ask. Is the converse true? If you have isomorphic spaces, does that mean that the spaces are homotopy equivalent? So we've shown that homotopy equivalence of spaces implies pi 1 of x is isomorphic to pi 1 of y. But now we're asking, what about the converse? Well, can you think of two things that are the same pi 1, but the spaces feel very different from each other? I've already said that pi 1 of S2 is trivial. 0, 1 orientation trivial is. Here's something else that's trivial. Pi 1 of a single point, right? But let's think about the maps from S2 to a point, and the map from a point to S2. Well, this is the dumb map, the constant map that sends everything to the point. And this is the map that just includes the point into S2. And you kind of have to pick those maps. There's nothing else to do. Let's think about the compositions. Let's see if this is a homotopy equivalence. What is phi of C? So this is, first you're going to send the point. You're going to include it in S2, and then just send it back to the single point. Well, that just is the identity map. So that is not a problem. That really is the identity map. That's good. How about the other direction? Phi takes S2. It sends all of S2 down to a point, and then includes that point back into S2. So this is the map that sends all of S2 onto a single point in S2. It sends all of S2 onto some point on S2. It sends all of S2 onto a point on S2. Is that map homotopic to identity? Yeah. We don't have the tools to prove it yet. But hopefully you can kind of believe like there's no way to continuously deform that to a single point without breaking it open in a continuous way. So this is not isomorphic to identity. Phi composed with C, I mean, it is not homotopic. It's not homotopic to the identity map. It's not. So S2 is not homotopy equivalent. Not homotopy equivalent to a point. So the converse fails. So although whenever 2 point spaces are homotopy equivalent, that means the spaces are isomorphic. You could have spaces that are isomorphic. You could have fundamental groups that are isomorphic when the spaces are not homotopy equivalent, right? Which means you might want to try and find a more general description and keep going. But for today, we're just going to stop with a conclusion that whenever two spaces are homotopy equivalent, that means that the fundamental groups are isomorphic.